Alejandro, cuando los hayas aceptado.
Cuando Ivonne me diga, empiezo a admitir.
Ya estamos en YouTube en vivo.
Ok, ya están admitidos todos.
Muchas gracias. Vamos a esperar unos momentos. Ok, muchas gracias a todos ustedes por estar aquí con nosotros en el seminario de Ciencias Atmosféricas para quedarse en casa. Es un placer que nos estén sintonizando, ya sea ahora en vivo o después por medio de la transmisión de YouTube. Muchas gracias. El día de hoy tenemos una invitada muy especial que se llama la doctora Annareli Morales. Estamos muy emocionados de que haya aceptado nuestra invitación. Ella nos va a presentar la ponencia titulada Métodos estadísticos para explorar las variables físicas y medioambientales en la precipitación orográfica. Y les voy a contar un poco acerca de la doctora Annareli. Ella estudió la licenciatura en Ciencias Atmosféricas y Geología de la Universidad de Illinois en el 2012. Después hizo su maestría en Ciencias Atmosféricas en la Universidad Estatal de Colorado en el 2014. Y también tiene otra maestría en Ciencias Oceánicas, Atmosféricas, Oceánicas y Espaciales en la Universidad de Michigan en el 2016. Y en el 2019 obtuvo su doctorado en Ciencias Atmosféricas, Oceánicas y Espaciales de la Universidad de Michigan. Actualmente ella es postdoc en NCAR, el National Center for Atmospheric Research, que está localizado en Boulder, Colorado. Y también me gustaría compartirles que yo entré en contacto con ella porque un investigador que suelo trabajar con él en NCAR, que se llama James Dunn, le sugirió a ella que me escribiera y empezamos a intercambiar un par de emails y ella me contó las ideas que tenía acerca de la precipitación en el suroeste de México. Me pareció fascinante y hablamos de que a ver si podría venir algunos días en el Centro de Ciencias de la Atmósfera. Para eso ya tiene como 1 año y medio. Pero bueno, nos cayó la pandemia y pues ahora estamos aquí, la tenemos aquí con nosotros y esperamos que en un futuro nos pueda visitar en el Centro de Ciencias de la Atmósfera. Bueno, pues sin más preámbulo, adelante Annareli. Es todo tuyo el espacio para que nos compartas tu presentación.
Muchas gracias. Voy a ver si puedo compartir. A ver. ¿Pueden ver? ¿O qué ven, pues?
Sí, veo tus diapositivas. Ya lo ven en pantalla completa.
Ok. Oh, ok, perfecto. Bueno, hola a todos. Gracias por estar aquí y por escuchar. La plática va a ser en inglés porque mis padres son de México y me enseñaron español, pero yo no fui a la escuela o no aprendí estas cosas en español, entonces no podría explicar todo en detalle si lo hago en español. Entonces voy a cambiar a inglés. Bueno, hi everyone. So today I'll be talking about statistical methods to explore environmental and microphysical controls on orographic precipitation. I am an advanced study program postdoctoral fellow, and my co-authors are Derek Passelt, Hugh Morrison, and Fei He. So to start, so orographic precipitation, it's in the title. What is it? What does it mean? Orographic precipitation is precipitation that's generated or modified through the interaction of moist airflow with topography. So here we have a mountain range in the background, and in the foreground, you have mountain range full of snow. But in the foreground, we see that it's pretty dry with a small area of water. And so what we like to say, it's snow in the mountains, means water in the fountains. That's why orographic precipitation is very important to us, especially in the western US or anywhere where there's mountains. That snow that's in those mountains can be stored as fresh water and in the winter, and then in the summer it can melt and provide water resources for agriculture, for recreation, and so forth. But here we see that sometimes there's not enough precipitation that falls out, and so our reservoirs could be depleted. But sometimes we actually get too much precipitation from mountains. And in those events, you can have flooding, you can have destruction to roads, bridges, etc. And so here's a picture of one of the floods, or the 2013 flood that occurred in Colorado, in Boulder, or a lot of it happened in Boulder, but it was a lot of the state. And so precipitation over mountains is very, very important if you have too much or if you have too little. And in general, looking just globally, orographic precipitation is an important freshwater resource to over half of the world's population. And with climate change, water supplies may become limited, which can lead to conflicts for water rights. And some of these conflicts have already been going on. So in general, we want to, or we need to better understand orographic precipitation processes and improve their representation in numerical weather and climate models. And there are many ways to get orographic precipitation. But for my work, I study, or I focus on moist neutral flow. And so that's flow that when it encounters a barrier, it poses little to no resistance to mechanical lifting. So the air just kind of follows the barrier and gets lifted. And with it, if there's enough moisture and enough vertical velocity, this moist air can cool as it rises and clouds can form. So this kind of moist neutral flow characteristics is typically associated with an atmospheric river. And what is an atmospheric river? These are very long, narrow regions of strong water vapor transport. So here we have a global picture of the column integrated precipitable water in these bright yellow orange colors. And we see that this one ribbon that comes out from the equator source of moisture is going from the equator towards the mid-latitudes, and it's impinging over California. And so that would be the atmospheric river. They can carry or transport over 2 times the flow of the Amazon River. So there's a lot of water being transported around. And they're usually found ahead of the cold front of an extratropical cyclone. They're most frequent during the winter months of each hemisphere, and the landfalls frequently coincide with complex terrain. And so when this moisture then interacts with topography, there's precipitation that can occur or be enhanced. And observations of these atmospheric river events making landfall show there are multiple meteorological controls on orographic precipitation from these atmospheric rivers. So one of them would be what's coming in, what are the ingredients, the upstream environmental conditions, how much moisture is there, how fast is the flow, how stable is the flow, how, or what is the stability of the flow, other temperature, various environmental conditions. So in your model, if you were trying to forecast this, it'd be the initial conditions. And then once this air encounters the mountain and a cloud forms, well, what is the temperature? How high is the level of the freezing level? That can impact what kind of precipitation will fall. And then the microphysical processes that happen inside of the cloud are also, we need to understand those. Are we getting snow? Are we getting ice? Melting? What processes are happening? So these are the main things that are controlling the orographic precipitation. And so given that information that we know orographic precipitation is important, and we want to understand how these controls, these environmental microphysical controls impact precipitation over mountains, my science questions are how do these different controls impact orographic precipitation at the surface, which microphysics and environmental controls are the most important to precipitation, and what are the relationships or interactions between these controls. And so to do that, we use various statistical methods and modeling. Because I can't perturb these parameters or these controls in the real world, I have to use a model. So my framework is, I use an idealized modeling framework to simplify the system and help us understand the processes. So we use the Cloud Model 1 or CM1 model by George Bryan here at NCAR. That produces idealized simulations, and we basically feed the model a simplified atmospheric river environment, and it's a sounding that came from an atmospheric river event that it was observed during the Olympic Mountains experiment in Washington, in the US. And so we have our environment that's atmospheric, an atmospheric river environment that's moist neutral. You feed it into the model, and you have a very simple bell-shaped mountain, and you get precipitation and clouds to form. And then from there, once you have your control simulation, we want to figure out, well, what environmental parameters are important, and answer those questions. So we look at environmental parameters such as wind speed, temperature, stability, relative humidity. And we also look at microphysical parameters such as particle fall speeds, density, collection efficiencies, and various processes associated with warm rain and ice processes. So this is what we're using, I guess, our tool, modeling tool, and these are the parameters we're going to be testing. But the first words in the title were statistical methods. So what kind of methods do we use to understand how these parameters control the precipitation? Well, we do sensitivity analysis methods. The first kind of method is a single parameter perturbation. This is the most commonly used in our field to understand how sensitive is your model output. So let's say precipitation at the surface, to perturbing a parameter within the model. So here you perturb one parameter at a time while keeping the rest constant, and it helps you understand the physics. So I have one example. Let's say we're perturbing the snowfall speed coefficient within the Morse microphysics scheme in the model. So the Morse microphysics scheme is what I use and what I analyze because I work with Hugh Morrison. And within that scheme, there is a equation that describes how fast the snow will fall out. So the snow particle fall speed, or V sub S. That relationship is a power law that contains an A coefficient and a B exponent and a D diameter. So there's a relationship between how big the particle is and how fast it will fall. But there's also this A sub S parameter. And the A sub S parameter, it's basically trying to describe the complexity in the habits of the crystals. So you have all these kinds of crystals in shapes, but in the model or the microphysics scheme, we have to simplify everything. And so it's really just represented as a sphere, but to represent the possible changes in how fast the particles could fall because of their habits, you could have different values for A sub S. And so changes in A sub S can directly affect how fast the snow particle falls. So we know that's what's happening in the model, but how does it actually affect the precipitation at the surface? And so we, for the single parameter perturbations, we have one parameter, A sub S. We have a control value, that's just the default setting in the model. And then we have some minimum or maximum range of uncertainty or variability in this parameter's value. We then perturb the parameter within that range and see what the response is for precipitation. So here we have on the y-axis the precipitation rate, and the x-axis is the A sub s parameter. So going from, or that middle line in the center, the vertical line shows the control value. So if you just focus on the green and the orange lines that are in bold, those are for the top of the mountain. So if you have your fall speed coefficient get bigger, so you have a larger fall speed coefficient, then your precipitation rate is increasing over the upwind top, but it decreases over the downwind top. So we're affecting where the precipitation is falling. And so here's a diagram to kind of illustrate what's happening. So you have your mountain, it's precipitating over the upwind side. If you're increasing A sub s, that means your fall speed of the snow is faster. So it's going to fall right on the upwind side. And that's what we're seeing on the upwind top. As you increase AS, because the fall speed is increasing, you have more precipitation falling out in this region over this spatially averaged area. And then if you decrease AS, so that means that your fall speed is a lot slower, the snow can be advected more easily to the downwind side. And so we see the same thing in the downwind top. As your AS increases, so it gets faster, it can't be advected because it's falling so fast. And so it just falls on the upwind side. So perturbations to the value of A sub s induce these large sensitivities on where precipitation falls. So this single parameter perturbation helps us to understand the physics and how are these parameters actually impacting our output. But perturbing a single parameter is inherently limited. This does not allow for possible relationships or mitigating factors that may exist. So for example, stronger winds have been shown that they can compensate for reduced moisture in observations. So if you have an air mass that doesn't have that much moisture, if the winds are stronger, it can produce the same amount of precipitation as if there was enough moisture. And additionally, I've done studies, and so have others, that have shown that precipitation sensitivity to microphysical parameters can vary depending on the environmental conditions. So if you have an environment that's maybe a lot colder or a lot warmer or a lot windier, that can affect your actual response by the precipitation. So maybe the snow can't actually make it to the other side because something else is happening. So because there's all these parameters that might be interacting with each other, an additional method, or we're increasing in complexity, would be to use the multi-parameter perturbations. And so this would allow you to perturb multiple parameters simultaneously to understand their interactions. And this kind of method also helps you screen out less important parameters. This is more of a qualitative analysis that you can use first before you add a more complex, computationally expensive methods. So the method that I used for my study was the Morse one at a time screening method, or MOTE. So this method simultaneously perturbs all the parameters. It performs these one at a time or single parameter perturbations for different points within the parameter space, and that allows for the possibility of nonlinear interactions. It allows for testing of large number of parameters. I tested 19 of them while being computationally efficient. So it didn't really, I think I had maybe 400 core hours that I used, if I'm not mistaken. So it's really fast, depending on how fast your model runs. And then it screens out input factors that are least important to your model output, depending on what your model output is. For me, it was precipitation rate. And so the way it works is you have, let's say here you have two parameters. You have a range of values within each parameter, and you randomly pick one value for each, or for parameter one. So you have 1/3 for x1, and then x2 is 0. You just randomly pick the value. So then you run your simulation and you get an output. You do this again for the next simulation, or run number 2. You can perturb that x1 parameter, and then you'll have 2 simulations where x1 is perturbed. And then you can do a third simulation where your second parameter is perturbed, but the other one is kept constant. And so this, you can keep going with this for however many parameters you have. And this initial position, I guess, within the parameter space can be changed. So you can pick another location and do the same thing. So you're testing within this, here's like a 2D parameter space. You pick a point and then you move within it and see what happens to the output. And then you can pick another point and move within it and see what happens to the output. And so then you have these pairs of simulations that you can use to compare and calculate what this method calls the elementary effect. So it's calculating the ratio of the change of the precipitation rate. So how is your output or your model output changing compared to the change in your input or your parameter value? And you then get these elementary effects. You get an ensemble of them because you're doing this multiple times. So here we did it 3 times. And you can then calculate the mean and the standard deviation of these elementary effect distribution to rank the parameters and determine nonlinearity. So I'll explain that a little bit more here. And one example is precipitation rate results for the upwind top. So again, here we are on this side of the mountain, upwind top. In the picture on the bottom left, it's the very top of the mountain to the upwind side. And here I'm showing on the x-axis is the mean of the elementary effects, and the y-axis is the standard deviation. And this is for precipitation rate. And each one of these circles represent the 19 parameters that I'm looking at. So 16 of them are associated with relative, or 15 are microphysics parameters, and 4 of them are environmental parameters. And you don't need to know the names. I'll point you to what you need to know. So basically the way you can understand this is as you get larger mu star or mean, it means that this parameter has a larger influence on your output. So a large mu star means that your parameter caused a large change in the output. So here the output of the precipitation rate. On the y-axis, the larger your sigma is, the more interaction there is between that parameter and other parameters. So large sigma means parameter resulted, or perturbations in that parameter resulted in a larger variety of output values. And this is what we call nonlinear effects. So this could be because 2 parameters are have a relationship together, so they're interacting with each other, or because one parameter happens to be nonlinear, or has a nonlinear effect on your output. So that would be like if your snowfall speed coefficient, it didn't just go up, or it didn't just have an increase in precipitation over the upwind top as you increase the snowfall speed. Maybe it went up and then back down. So that would be a nonlinearity. And here, using this method, we find that 2 parameters are very important. So they have a large influence and a large interaction. And these are the fall speed coefficient for snow, A sub s, that we already saw, and number 16, which is the relative humidity. So over this region of the mountain, the changes in the relative humidity, so that's the environment, can have impacts to the precipitation at the surface, just like, or as much as perturbing how fast the snow falls out, which is a pretty big deal because like if you don't have enough moisture, if you don't have the ingredients to create a cloud, and you don't create a cloud, then the microphysics doesn't matter, because there's no cloud to produce. But if you have a cloud, and then you also can perturb the parameters within that cloud, it can be just as impactful as the amount of moisture that you have, let's say. So this kind of method, this multi-parameter method, basically can narrow down which parameters are the most important. So we went from 19 parameters that include microphysics and environment, and that helped narrow it down to a smaller subset of 6 parameters. We still have environment and microphysics being important here, but now we can do a little bit more analysis. So previous studies demonstrated the existence of multivariate controls on orographic precipitation, but these are computed through forward sensitivities or forward models. So what I mean there is you have some parameter that is, its value is perturbed. So it's like turning a knob. And then you run your model with this perturbation and you see what happens to the output. But instead, if we're interested in a particular precipitation outcome, and then you want to know which combinations of parameters are most favorable for producing said outcome, then an inverse model is required. So that's the third, I guess, kind of method, sensitivity analysis method that I've used. And here we use Bayesian inference to determine which parameter combinations produce a given heavy orographic precipitation event. And this kind of method can provide insight on the parameter relationship. So try to answer that question of what are the relationships between or interactions between these parameters. So for this method, I use the Markov chain Monte Carlo, or a Markov chain Monte Carlo algorithm. And step 1 would be to figure out what your parameter subset is. I used that from the previous study. Then you produce a control precipitation rate distribution using the model. So, or you could have a real event, but for this, for my study, I used a simulated precipitation distribution. So here we have precipitation rate for the 6 regions over the mountain. So the peak is happening over the upwind top. And then you apply the MCMC method to find the parameter value combinations that reproduce that control precipitation rate distribution. So the algorithm is shown here, but basically what MCMC does is it performs repeated random sampling of here a 6-dimensional parameter space. And the algorithm can frequent higher probability regions while avoiding lower probability regions, since not all combinations of these parameters could produce this precipitation output. And so we use this method for the parameters to understand the orographic precipitation relationships to these parameters. So one of the results was that different combinations of environmental conditions and microphysical parameter values can yield similar total precipitation rates. So here's one example. This is the kind of output that we get from an MCMC analysis. So the x-axis is your snowfall speed coefficient, and the y-axis is a wind speed factor. So it's increasing by 2 or like plus 2 meters per second or minus 2 meters per second. And basically it's as you go up in the vertical direction or in the y-axis, you have a faster wind speed. And in the x-axis, going from right to or left to right, you have a faster snowfall speed. And the colors represent the probability that this combination of parameter values could produce our desired outcome. And so here we see that the yellow colors are kind of forming a generally positive relationship. And that means that the horizontal wind speeds would need to decrease. So the overall winds would need to be slower in order to compensate for snowfall that's falling slowly. Otherwise, your snow would end up in the wrong location. So that's one result that we found of these relationships. And the second one would be that their parameter relationships exist for different environmental regimes. So within this result, we see if we just focus on relative humidity that's, we call it dry, so it's between 85% and 92.5% at the surface. The relationship between these two parameters is really, it only captures part of it. So you have a lot more sensitivity in the value of the wind speed. So you can't go too far, too fast or too slow within this dry regime, because then you won't be able to produce the precipitation output. You have to stay within this very narrow region because it's so dry. And then when it's moist, you can be a lot slower. Your winds can be a lot slower to still produce the precipitation output. And again, there is some relationship between the fall speed, but there's something going on between all these three parameters. And so we can describe it simply by saying, to get the control precipitation distribution that you're looking for, if your relative humidity is decreased, then you would need to increase the wind speeds to compensate for those parameters. And that's what we see in observations, as I said in the beginning. But if your wind speed is now increased, then your snow would need to fall a lot slower to land over the appropriate subregion. Otherwise, it's going to fall somewhere else. And so these mitigating factors between the wind speed, the relative humidity, and the snowfall speed, or there are mitigating factors between these parameters. The first two are strongly tied through dynamics, and then the wind speed and the snowfall speed are tied through horizontal transport. So you have to take both into consideration. And so to summarize, the sensitivity analysis helps us understand the impact of perturbing microphysics, model parameters, and initial conditions on orographic precipitation. Multi-parameter perturbations need to be included to account for nonlinear relationships. And there's different methods that exist to explore this parameter space, or your parameter space, whatever it could look like. One of them is MOTE, and one of them is the MCMC that I used. And to better understand the environmental microphysical controls on orographic precipitation, these novel sensitivity analysis methods have been applied, and we found a small subset of parameters that are really impacting the precipitation. And these methods also let us see the relationships between the parameters and how it's really complicated. And basically you need to incorporate, or if you're trying, let's say if you're trying to run an ensemble and you want to understand the precipitation impact, you need to also incorporate the microphysics and how that's changing, not just the initial conditions, because everything can interact with each other. And so I'm out of time, but I wanted to just show a slide to refer to what Christian was saying earlier. So I am very interested in looking at precipitation in southwestern Mexico. I just haven't gotten a chance to do it during my postdoc, but I'm hoping to do that during my new job. And so my family is from Pantla del Zapotal in Ceja Blanca in Guerrero. And I'm really interested in precipitation variability in the state of Guerrero. What does the diurnal cycle look like? How has it changed? All these details for this specific region. And this animation was just showing a very high resolution MPAS model simulation. And there's so much detail happening and so many things that I want to understand to better help my family, who are all farmers in the region, and they rely on the precipitation. And they have things that they've noticed. And so I want to talk to them and understand what have they seen in the decades that they've been farming meteorologically that has changed. And then additionally, I have an idea that I've been talking about with a bunch of people at NCAR, where NCAR has various kilometer scale climate runs. So we have one called CONUS, which covers the US, and they're 4-kilometer simulations of using WRF, and they're 40 years into the past. And so you have this giant data set that then you can use to do even finer scale simulations. And so they have runs over the US, and they have runs that are starting over South America, but they don't have anything to cover this gap. So if you're interested in talking more about how to fill in this modeling gap, please let me know, and contact me if you're interested in any of these kind of ideas. I'd love to keep talking about them. All right, that's all I have. Thank you.
Thank you very much. So we are going to start right now the question section. So first I'm going to explain in Spanish and then in English. Muchas gracias a todos por escuchar esta muy interesante plática, y muchas gracias a Annareli por esta plática tan interesante. Los invitamos a que los que estén interesados en hacer una pregunta la pueden hacer de preferencia. Si es muy técnica, tratar de hacerla en inglés. Si no, la pueden hacer en español, y tratamos de pronto traducir algunos términos que de pronto puedan ser confusos. Pueden levantar su mano, dependiendo de la versión de Zoom que tengan, en el chat, o en la ventana de participantes encontrarán un botón de levantar mano, raise hand. Entonces, por favor, levanten la mano. For all of you that don't speak Spanish, your questions are very welcome. Please, you can find a button, a raise hand button in the chat or the participant section. It depends on your Zoom version. So please, you're very welcome to raise your hand. Right now we have a question from Brad. So Brad.
Hi, Annareli, can you hear me?
Yes, I can.
Hey, great. Very, very nice talk. I think it's so interesting. I think it's a simple question, but maybe the answer is a little bit complex. I don't know. So one of the things that I noticed in most of your talk, you talked a lot about snow.
Yeah.
And, we know, particularly for Mexico, that so much of the precipitation is not snow when it reaches the surface. Obviously, a lot of it still forms as snow in the microphysical processes aloft. But I was curious if you had a lot, to look at that, and if you had a chance to look at that process in temperatures above 0 Celsius, and what you might think your findings mean for kind of warm rain processes, or warm rain processes, maybe not, but just snow that falls and then melts as snow and falls as rain when it reaches the surface.
Yeah, that's a great question. I have not looked into that. That would be something that would be super interesting to do. It would be a lot different, just model configuration wise, because everything I do is set for an atmospheric river. And so it's 2-dimensional. But then if we're talking about more maybe convective kind of precipitation that we see in Mexico, we might have to switch to 3 dimensions. But regardless, I think some of these interactions, or I don't know what would come out of it, I guess, how the sensitivities would look, but even in these environments, the freezing level is pretty high. It's about 2.5 kilometers high, and so 2.5, I think, or 3. So there's a lot of melting that happens. So not all of the precipitation falls as snow. Some of it does, but there's still a large percentage of the total precipitation that falls as liquid. So I think some of the results could be applied, but if the precipitation isn't moist neutral, we'd have to redo this whole study with convective precipitation, which I would love to do. But yeah, that's a good question.
Thank you very much. I agree. I think it's a really interesting kind of question to take the applicability from snow and then expand it out to other, microphysical, well, for rain microphysical processes. Thank you very much.
Yeah.
Thank you, Brad. Anyone else? So while if any of you want to ask a question, mientras alguien quiera animarse a preguntar, voy a hacer una pregunta. So this is perhaps a very silly question, but I'm really curious about so in this case, you are producing snow by orographic forcing, but it's how this analysis may change, or how this microphysics might be affected if additionally to the orographic forcing, you have like a synoptic forcing, for example.
That's a great question. Continue.
No, that's not the main question.
Okay.
That's
yeah.
just a curiosity.
Yeah, I think that's a great question. I'm not sure how it would impact it. I don't want to speculate, but yeah, that's a good point. This was just orographically lifting and producing precipitation, but in the real world, yeah, we have synoptic clouds, or I guess in the West Coast, we have something called the cedar feeder mechanism, where you have a upper level cloud deck that's snowing, or ice crystals are falling in, feeding or seeding the lower level orographic cloud, and they tends to cause enhancement in precipitation at the surface. And so I think it would be, I guess basically the way I was working on this for my PhD was, let's start with an idealized framework and then start adding more complexity to it. So an additional complexity you could add, or realism you could add to this kind of study, would be adding the synoptic component, or including a more complex terrain. So yeah, that's a great point though. I'm not sure how that would impact it. I think we would see a lot more different processes at play because of that cedar feeder mechanism. And there might also be, not sure. There's so many things that can happen. I don't want to speculate. But yeah, that's a great idea.
Thank you very much. Somebody else want to ask a question? Por favor, si quieren hacer una pregunta, la pueden hacer también en español. No sean tímidos.
De lo que sea, de lo que quieran hablar, puede ser de lo que presenté o de new stuff.
Hay una pregunta.
Yeah.
Hay una pregunta en YouTube de Graciela. ¿La podría leer, Ivonne? Ok. Ivonne no puede prender su micrófono. Okay, I'm reading the question right now.
Yeah.
So, Dr. Graciela Raga asks, hi, Annareli, thank you for your presentation, very interesting. I work at CCA UNAM, so she's the leader of our group, where Christian and I work with. And she is very interested in the precipitation in the southwest of Mexico and in Oaxaca.
Ooh, yeah.
And she said that the synoptic scale is very important there, particularly in the extreme precipitation events, So she will be very interested in talking to you.
Yes, I've read a bunch of your papers, and I have seen some really awesome stuff you've done with radar and the limited amount of radar that is in that region, and it looks amazing. So yeah, please let's schedule something and talk more about this. I would love to basically get info or knowledge from people that study the region, have studied this area for that for a long time, or have lived the synoptic and orographic influences of this region. Because I visited there many times, but I have not lived there. And from the times that I have visited, I have many questions about precipitation because I don't understand it.
Okay. Doctora Telma, the director of our center, she wants to ask a question, so I'm going to unmute. So Doctora Telma, you can talk right now. Okay.
Creo que
ya le activé, sí.
Bueno, ya, nada más tengo habilitado el audio.
También.
Pero no importa, no importa. Muchísimas gracias. Ok, ya déjame que ya me habilitaron todo. Bueno, muchas gracias, doctora Morales. Es un gusto haberla tenido como ponente. Y pues y le agradezco mucho que pues nos ayude a seguir dando este tipo de conferencias para todo público y sobre todo para los estudiantes, ¿no? Quizás yo diga una pregunta un poco sin chiste, pero me llama la atención. ¿Usted cree que la precipitación es en un lugar específico o una región, depende más de la orografía que de las condiciones sinópticas?
Buena pregunta. Si está bien, voy a responder en inglés. I think it depends, because the synoptic environment that's bringing in all the ingredients and this basically setting up the precipitation. So if you let's say you have some extratropical cyclone coming over and you have this big cloud and it's coming, I think that would be, it's maybe not which one is more important, but it's different, like primary versus secondary. They're both very important.
Okay.
And I think it might affect, it depends on, are you interested in a long-term understanding of precipitation or short-term? If it's short-term, then maybe those orographic influences would be very important, because you'd have like different valleys where water would fall, or different turbulent eddies or flow within canyons or whatever that can impact the precipitation distribution. So I think long scale, perhaps these details wouldn't be as important. It would just be the synoptic environment that's coming over. But that's a really good question. I'm not sure if I've seen that be explored. And I guess also just I'm looking at my presentation and I'm just staring at the map of the US, and we have very there's a strong or a big ridge of mountains. But in Mexico, there's all these mountains that crisscross each other. And so how to figure out the influence of synoptic versus orography when orography is everywhere. I guess you would just have to maybe run a simulation where you just get rid of all the mountains and see what happens.
Okay.
Thank
you very much.
Thank you.
Okay, bye. Thank you.
Thank you very much. We have another question from Janet Diaz. She asked, are there implications of this mitigation of different parameters like RH, AS, U for model parameterizations. Perhaps Janet may want to elaborate on this question. Janet, may I going to ask you, you can turn your microphone on.
Hi.
Hi.
Thank you. Yeah, my question is if you find the different relationship between these parameters, the environmental and the microphysical. So my question is, does it have implications for model parameterizations?
I think so. I wouldn't be, I guess yes and no. Yes, because the A sub S parameter is part of the microphysics parameterizations. And so because it's so important, I guess I'm trying to communicate that this parameter is important. And so the value of this parameter is important. And if we just leave it constant, then maybe we're not incorporating the uncertainty within the system that we could be incorporating. So understanding more or using observations that we may have to understand better the values of this parameter. Where is it coming from? What is the range? And then including those parameter ranges or the values within this range when you're running an ensemble. So perhaps you could run an ensemble with your uncertainty and your relative humidity and your wind speed, so your initial conditions. But you could also create ensemble members where your fall speed may be different, or the coefficient might be different, or any other parameter, and see if that increases the spread of your precipitation to include what would actually occur. And so that's, I guess, where I'm leaning towards yes, in a way, but no, because I don't think it would be a good thing to parameterize this relationship between RH, AS, and U, since RH and U are large scale things that can be directly measured, and AS is, it's basically coming because we have to parameterize microphysics because it's so small scale. So I think basically the implications of this result is that we need to account for the uncertainty and or variability within these parameters if we're trying to forecast the precipitation for these atmospheric rivers. Does that make sense?
Thank you very much. Maybe I text you later. And thank you for your talk, for your presentation.
Thank you very much. We have time for a last question, and it's from Guillermo Montero. Perhaps, Guillermo, do you want me to unmute? I'm turning your microphone on.
Yes, thank you, Alejandro. Hi, Annareli. Very interesting your talk. I have two questions. The first one is, what are the key microphysical factors that controls or affect the AS parameter? And how do you relate these factors with the microphysical parameters such as size and number of ice nuclei or CCN?
Let me see. So if I'm understanding, you mean, so for the AS parameter, so I guess in the microphysics scheme that I use, which is the Morse scheme, the AS parameter is just one number. And it's some default number that I'm not sure where it came from. That's just a default that comes in the scheme. And that's just set. Nothing can change that value of AS unless you change it. But that parameter can then influence how fast the snow falls, and that has impacts on key, I guess, microphysical processes. I think that's maybe, I'm not sure if I understand completely, but AS.
Sure.
is not changed in the schemes.
I mean, as controls in some way, this parameter is related with the fall velocity. So the fall velocity is also related with the size of the hydrometeors, which will be also related with the size of the initial CCN or icing.
Mm-hmm.
So how do you think that is? Can you control this number in the model or not, depending of your initial spectra, size spectra?
Yeah, that's a really good point. I did not look into also perturbing aerosol characteristics, but that was something that I did want to do. I just never got to it. But yeah, that's a very good point. If you're changing the ice nuclei, so the number, because in the Morrison scheme, you don't have that capability. I don't think so. You can change the CCN number in a proxy way by changing the number concentration of cloud droplets, of the initial cloud droplets. And so you can change that. And I haven't done a multi-parameter analysis of changing the CCN and also perturbing the other parameters. But I have done just like a single parameter analysis of CCN, and the bigger or the more CCN you have, so higher number concentration, your precipitation is increasing, I think. Actually, let me not say anything about that because I don't want to misspeak. We can talk about those results later. But yes, I think that would have an impact. I just don't know how, or at least I can't think of it at the moment. But that's a really good point. The Thomson scheme in WRF, and I think it's also in CM1, does have the capability to perturb the ice nucleating particle concentration. So this analysis could be done again, but then using the Thomson scheme instead.
Okay, thank you very much for your answers, and probably we can talk later also.
Yeah.
Thank you.
Thank you very much. We don't have more time for questions. I know that you may have more questions, so you can write to Annareli. Here in the presentation is the email, so you can write to her and ask her questions. Just a final comment by Graciela in YouTube, that she's watching us there. So I'm going to give you her email so you can be in contact. And she says that in terms of the gap in simulations in Central America that you mentioned, there is the Cordex project that also has some long-term simulations that you could look into.
Awesome. Okay, thank you. I will email you and get all this info. Thank you.
All right. Annareli, thank you very much. We are very happy that you were today with us and you accepted our invitation. And now Christian is going to say some words.
Annareli, thank you so much for your presentation. I really enjoyed your work. It's amazing. Congratulations, by the way. And hope to have you here in a new future. And for those of you that are from Mexico, from Latin America, you can follow this list. Y por supuesto, se pueden inscribir a la lista de seminarios de Quédate en Casa. Ahí van a recibir la información de todos los seminarios que estamos preparando. También si tienen alguna idea que se podría presentar en este seminario o algún tema que ustedes quieren presentar, nos pueden escribir al email de Alejandro o a mi mail enviando una propuesta de título de la presentación, del resumen y un CV corto, y nosotros por supuesto les responderemos con mucho gusto. Y también tenemos una revista que se llama Atmósfera, para todos ustedes que no están muy familiarizados con esta revista. Es Open Access, también tiene una sección que es Early Release. Entonces, inmediatamente de que es aceptado, se pone en línea y ya puede ser citable también. Es importante mencionar que en esta revista se pasa por un proceso de peer review, entonces, pues para que la tengan en cuenta, también tiene un buen factor de impacto y pues obviamente no cobra, es gratuito. Y finalmente, pues los quiero invitar a todos ustedes al seminario de ¿Qué onda con el tiempo? Que se lleva a cabo los días jueves a las 5 de la tarde, cada 15 días, por Alejandro, por mí, por el maestro en ciencias, Orlando Peña. Y también tenemos otro seminario que se llama el Seminario Institucional, que también es llevado cada 15 días. Pero estos seminarios son cada 15 días los viernes a mediodía. Entonces ahí ustedes van a poder encontrar toda la investigación que se hace en el Centro de Ciencias de la Atmósfera. Y pues muchas gracias por acompañarnos en este seminario. Nos vemos hasta la próxima.